many memories.
Yes. So yes, welcome back, folks. Hello, everybody. Is it still raining outside?
No.
No? Hooray. Good.
On and off.
On and off?
Like 30 seconds.
Okay, well, I don't have my umbrella, which guarantees that when I leave today, it will be raining, so
It's supposed to be.
that's what happens when you don't pay attention when you leave in the morning. So I sent out a note after class last time. I continue to juggle the schedule based on where we're at. My goal is to make sure that you have at least a week after we finish something before you're asked to complete a homework on it. So if we don't finish it in the amount of time I have estimated, then I'll keep bumping it down. So that's why after class, either today or tomorrow, I will put up another formative assessment quiz for you to work on. And then your first homework will not be due until the 23rd. So I did want to demo today how to get through SAS and Stata live rather than having everyone play along with me. That's what I would like you to work on Thursday when we have no class. So take the time that you would have spent, sit somewhere comfortably, grab a beverage of your choice, coffee or something, beer, whatever it takes to get through the session, and try to figure out how to log into these things and just make the program that I gave you run. Because that is the hardest part. And that's what I wanted to re-show you today. So the steps that I took, first thing is that I logged onto the virtual desktop using my Hawk ID and my Iowa password. And then there are apps. You can select, make apps a favorite if you know you're going to use them over and again. So that's where I got to my favorites. I started up SAS and I started up Stata. So we looked at SAS last time, so let's start that. So we have 5 windows that open by default. Over here is a results tree that you may or may not ever need, but the Explorer is where your stuff is, so you will need that. So one thing I helped several folks do right from the get-go is get it back if you accidentally close it. Uh-oh, where'd it go? Well, the good news is that it's always here. To get it back, there's a view option that lists all the things that you might want to view. You can select Explorer, but then it shows it on the other side. Now, there's nothing wrong with this, but it just looks different than what you're likely used to seeing once you get used to using this program. So to make it go back, under Window, there is a little option here for Docked. If you click that, then it goes back over here where it's supposed to be. So that's troubleshooting number 1. So when you're starting in SAS, first thing you want to do is open up your program. That's your syntax file. A syntax file is a set of instructions, basically, that the computer understands, the program understands. It's the .sas extension. For all exercises that I give you in terms of examples in class and homework, I will give you a starter SAS file. You don't have to create one. You'll just, that way we can make sure that the frustrations are minimized. So I'm going to go over here and open program and navigate to where my stuff is. So I keep everything inside my Dropbox, which is on my C drive. Let's see, it's inside this one. We're looking at example 2. So I open it and it shows up like this. The stuff at the top here is meant to customize what your output looks like. There's going to be 2 different types of output that are requested, and only one of them is what you're going to see in class, which is why I wanted to make this point. So do you remember what this keyboard shortcut is to make code go? Anybody? What, F3? Very good. The other option, the running man, cleverly posted next to the delete key. So try to avoid the running man if you can. So I have a bunch of notes here with respect to what SAS syntax means. What does it mean if you see red? Bad. Something is wrong. Correct. Otherwise, you'll get used to seeing the colors and they'll help you. So line 71 here, this is the first step. Tell it where your stuff is. So rather than saying, let there be light, I'm saying let there be file save, where file save is an abbreviation that I named. Other ones, sometimes I say file path, my files, my stuff, whatever name you want to put here, and to tell it where your directory is. If you're using the virtual machine, you need to preface your actual location with this. It's / /client/, and then in the window it tells you where it is. It uses a $sign instead of a colon here for reasons that I don't understand. It needs to be a colon.
So is this something that we'll do every time?
Yep.
Okay.
Yep. So I'm going to run that. And I know that it worked if I go to my log and it just took it and didn't give me any commentary. So blue and black are generally good, red is bad. The other piece here we didn't talk about, this is if you already have a SAS file, but I'm not going to have you work with those this semester very much, so we can skip that. Importing. So proc import is how you get other types of files in that aren't SAS files. In this place right here, there's two parts. First is the reference to the path that we just defined, the file save. When you want to refer to it, it's ampersand in front, the abbreviation that you chose, and then a period afterwards. Then a slash, and that gets you to the actual file. Note that it's in this pinky purple color, not very easy to see on the monitor here, but that means this is case and space sensitive. You have to get it exactly right. It wants to know what you want to call your file, and I'm choosing GSS from Stata as my name. The database type, it understands if I say DTA that it's a Stata file. And if I run that, hit F3. Now note at the top, it says proc import running. It takes a second. It will take more time for larger databases. This one's actually pretty big. So I know that it worked by two ways. In my log, it says this data set was successfully created. See, SAS is all about self-efficacy. Successfully created. Hooray! If I want to go look at it, I have to go over to my libraries. So that's my little file box here. Inside work is where it went. Work is a temporary directory. All of the data sets that you create in a session will be gone after you shut down SAS. That's not a problem. All you need is the original and the code that does things to it. You can look at your data set by double-clicking it. You'll see this one has variables that already have value labels on them. So it has imported the labels that were associated with the numeric codes for these categorical variables. That way they show up on your output rather than the numbers. You cannot do anything while your data set is open, so we'll have to close it back up again. Here's an example on how to import Excel, and this is what, if you wanted to do other data transformations, here's some examples. We don't need to worry about that. You can refer back to this example later on, or instructions on how to do various things. So I am going to, in this instance here, let's see, what do I need to do to make this work? I'm going to clear the labels out of it. Make a new data set and clear labels, that way I can have my own. Sometimes the ones that they do are less than helpful, and so I like the capacity to be able to do that. So here are two variables that we are going to work with in this example, marital status and education. I'm defining labels for these. Note that I'm putting the number that goes with it first. That way the labels stay in the same order as the original variable. So proc format, listing the values, run to make it go. So I'm hitting these things, and in my log, nothing has happened yet for output, but so far it's done everything I've asked and hasn't complained. This step associates the labels with the data set. So you'll note this combination occurs several times in my code, data and set. What that combination means is data is make me a new data set is from. So this is essentially save as itself, and then you're telling it to do things to that data set. The reason that you have to have this is that you can have more than one data set open in memory, and SAS has to understand to which one you want to make the transformations. So you can save it as a new data set if you want to do that instead, in which you would change the name on data to be something different. Set is where it's coming from. That's one of the main differences between Stata syntax and SAS syntax, is that Stata doesn't have this, because there's only one data set open in memory in Stata, at least up until the most recent version. So I will help you remember this in your starter syntax by giving you this part, and then you'll be asked, for instance, to make new variables, for instance, on this part. So here's an example of how a transformation that we might do. There's a variable in there called family income. It's in dollars, which means that it's a very, very large scale. If I wanted to rescale that to be in thousands of dollars, I can make a new variable. FamInc 1,000 equals the original one divided by 1,000. So the name of my new variable is here. The label, typo there, is associated with it here. So that way, when I look in the data set, I'll know all of the things that I need to know about that variable. So I'm going to run, let's see, this, where did I leave off? I did the formats. Going to run all that. Okay. Then there's just a couple things here that I gave you to get univariate descriptive statistics. We're going to do this again in the next lecture that we're just going to start today, so don't worry if I'm going too fast. We'll see it again and again and again. One thing that I'm doing to start off this whole thing, ODS RTF, that stands for Output Delivery System. It's sending your results out to a new document that you can open up in any word processing program. That way you don't have to navigate through the horrible virtual desktop to get your stuff back. So we're going to run a couple things here. First, let me show you what happens. Proc freq. That stands for frequencies. So this would be an example of how to get the number of people that are in each category for a categorical variable. So the ones that I've put in here from our GSS data set is marital status, as well as education. And I'm asking it to include missing values, I'm asking it to make pictures, and I'm asking it to use the formats that I created earlier to label the categories. So whenever you run a proc something, you need to run after it. Title is your option to be able to provide words that go in your output that help you keep it organized. If you want to shut it off, you just write title again, otherwise it keeps repeating itself forever and ever. By default, in new SAS, it's going to open up a 6th window, which is called Results Viewer, and it's going to look like this. So this is HTML output. You can save it and open it using any kind of web browser. It makes nice graphics. So for instance, these are the distributions for this sample of the number of people who are married, widowed, divorced, etc. It gives you the count, and it gives you the percent, and the cumulative gives you the total here. So in your first homework, I'm going to ask you to run similar descriptive statistics for categorical variables. This is what it would look like if you wanted a picture. This is what's known as a bar chart because each category is shown separately. Same thing for education. There are different missing value codes in this data set that are included here, and so that's why these first 2 letters are showing up. And this is the number of people falling into each category there. So this output is very pretty. You can actually ask for it to have different styles rather than, this is called HTML blue. There's one called like harvest, you know, it has nice fall colors. You can make it look like whatever you want. On the handouts that I'm going to make for you, your output is going to be the old school, what's known as listing, which is in this window right here. So it doesn't show you the plots, and it looks like just straight text. The reason that I use this still is because it's much easier to annotate. It takes up a lot less space. So it's not as pretty, but it's the same information. Status looks like this too, by the way. So, questions so far? All right, let me make sure that Stata doesn't get mad at me. Okay, it's still active. Sometimes if you don't play with it for a while, it locks you out. So proc freq is for categorical variables. There are 2 procs for quantitative variables. A basic one is known as proc means. Can you guess what that gives you? Exactly. So by default, it gives you mean, standard deviation, minimum, maximum, and n. So you list how many variables you want. I'm also specifying the number of decimals, so the output is nice and easy to read. So I'll hit that, run. Now I've got another table here at the bottom with that information. If you have a variable label, it will provide it. If you don't, it won't. And proc univariate gives you a whole lot more information. So I'm picking just one of our variables, FamInc in thousands. I am asking for a histogram. So I'm asking for a picture that shows the distribution where I tell it how many cases I want in how many bins. So I'm saying, okay, start with bins 0 up to 200, so that's 0 to 200,000 in increments of $10,000. And it's also going to estimate what the mean and variance are and show the normal curve overlaid. So if this were normal, this is what it would look like, is that curve. So let me show you what you get out of this, because it's all kinds of good stuff. So this one, it gives you more stuff. So moments of the distribution, mean, standard deviation, skewness, coefficient of variation, a thing I saw in the book that no one's ever asked me for. Kurtosis, thing I mentioned briefly that you don't need to worry about. The range, the mode, the median, so all the extra stuff that I mentioned one might want is in proc univariate. It also gives you percentiles for the distribution. And here is the picture that I asked for. So how would you describe this distribution? What words would go here? Skewed. Yes. Yep. Skewed positive. Yeah. Well, I'll go with bounded because you can't make less than $0. Although there was a comedian's bit I once saw. He was talking about being overdrawn in his checking account, and he's like, "I don't have no money," which was sort of funny to me. Like he hasn't gotten up to 0 yet. Like 0 is a goal to get back to 0. But yeah, these people don't have no money. And then there's these people, which I'm guessing that somehow this got capped. That's my guess, is that this is like 160 and above, and they check that box. So yeah, the normal distribution isn't a great fit for these sorts of data because of these extra observations out here. This is what it would have looked like if it decided where the bins would be. So the interval is in 8s rather than 10s, and it only goes up to 152. So it's pretty close to what I decided, but just keep that in mind that you can control the shape of the picture. And the same information minus the plots shows up over here in the listing output. All right. And then to make the handout that you're making through this ODF here finished, you run this one last part, RTF close. Come on, you can do it. And voila. No, really, it's gonna. It promised. And this is the file that I already put inside your folder, actually. So this is example 2 SAS output. There. So that HTML output shows up in a Word document. So I would recommend doing that once you're working on your homework and you've got the right models. You want to save the output for your reference to answer the questions. Then create a file like this. That way you don't have to go back into SAS or Stata to fight with it. So all I want you guys to do to start with is just take this file and try to make all this run. The only thing that you should have to change, which is what we worked on in class last time, is where your stuff is. This file save. Once it understands where your stuff is, you should be home free. Okay, questions? Now note, I don't know if you can see it right here, there's an asterisk. That means that I have edited the file and I need to save it. You don't have to do anything special to save your syntax files. The keyboard shortcut is Control-S. Under the File menu, there's a Save option. So just like you're used to normally saving your files, you do need to save the syntax, but you can do so easily. Okay. Questions? Okay, so I want to show you Stata because there's at least 2 of you who need to learn how to pledge allegiance to Stata, am I right? Mm-hmm. That's not my choice, but I like Stata fine for some things. I find it really annoying for others. It's you know, 6 of one, half dozen of the other, same as any program. So Stata has everything that it gives you in one window, the log and the output. So any information is going to be spit to one place, which makes it somewhat convenient. However, the syntax file is a do file here that opens in a separate window. So by default, it wants to open a data set. You have to scroll down to find the list of do files. I'm going to go and find it in my Dropbox again. There's example 2. All right, let me see if I can make this bigger. Zoom in. No, really, zoom in. A lot of zoom. So I tried to make the exact same file in Stata that I had in SAS in terms of the information that's in here. In Stata, there is no bad color. Red is actually reserved for labels, so anything in quotes shows up in red. So there are fewer colors to help you, but it's still the same concept. Anything in green is being read as a comment. You have to have an asterisk in the front. Anything that's in this sort of navy blue color is a system command. And all of Stata is case sensitive. So all of Stata's commands have to be in lowercase. And when you refer to your variables, they have to match the exact case that you've defined them as. There are no semicolons. It assumes that once you get to the end of the line, it's done. If that is not true, if you have a line that's really, really long and you want to wrap it, you have to have 3 slashes to tell it to continue. That's just the rules. Here's my analog to global. Let file save equal. There's no equal sign, but otherwise the syntax looks the same. If I want to use Stata inside the virtual machine, I have to add this part. Yeah, so this is, as opposed to having the program on your desktop directly, which I have a copy of when I normally am doing this, so that's why I had to change the path. I also have, by default, it only prints so much output and it makes you hit return before you get more. That's annoying, so I'm going to highlight that top part that shuts that off. The keyboard shortcut in Stata is Control-D to make it go. And then it just echoes back whatever I typed with a dot in front of it. If I want then to define my path here, come on, that, Control-D, then I have to go back to this. It looks like it's fine. Nope, hasn't gone yet. Hang on. Control-D, go. Okay, doesn't want to go. Okay, Stata, you're making me angry. I'm doing a demonstration here. It's like, yeah, I don't care. Oh, there it goes. See? It says, Stata needs attention. Mommy, Mommy, I need you to listen to me. That's what Stata's saying. Oh. I'll say it needs attention. Stata, did you wet your bed again? Is that the problem? Is that why you're hiding in the corner? I give up. I can't even. Like, seriously. Well, just pretend that there's stuff in the window. So the commands to do things are remarkably similar. Can you guess what this does here that starts with use? Yeah, bring it in, right? It's like import, but for a Stata direct file. Stata will accept fewer types of files than SAS. It will only accept a few different kinds, and so I'm probably going to give Stata files because Stata can go into SAS easier than vice versa. Label define is how you define value labels. Label values is how you put them in the data set. Gen is how you make new variables. So it's the same in principle, the new variable on the left side, the old variable on the right side. To save your output, what you're doing, that's log using. And so I'm starting a file to save all of the stuff that would come after it. No, we're not going to do that. Okay, that's fine, Stata. Display as result is the equivalent of title. Tabulate is like proc freak, it's like make a table of the values of these categorical variables. Summarize is the analog to proc means and proc univariate, depending on whether you want detail. That makes it look more like univariate. And histogram is how you make pictures. I'm asking it to save the picture here, and then log close closes the file. So if you were to run this and Stata didn't need this much attention, you would end up with example 2 dot, this one right here, .log is a log file, and this is what it will look like. It's just a text file that has an echo of all the syntax that it read in, as well as the results that follow. So that's helpful because then you don't have to flip back and forth like this table was generated by this line. And this you can open up in any Word or like Notepad, WordPad, any of those sorts of text editors. So, there. See? Take that. So, again, what do you have to change to be able to use this program?
Programs.
This one thing, Mr. FileSafe. Tell it where it is. In the future, you may have to change the name of the data sets, but we'll get to things like that. All right, so questions? Yes?
If our files are saved in work, if I close the virtual desktop, it will be gone.
I believe so, yes. So you will, if you make changes to this syntax file, you want to save those. And that's just Control S or file save, and that saves it to your hard disk. When you do transformations to the data set in Stata, I can't show you this, but when you close it, it'll ask you if you want to save those changes. You don't need to.
But actually, I did save it, and then when I go back, it's in the work file. There's
In Stata or SAS?
SAS.
In SAS, yes. So the work folder dies at the end of each session in SAS. So you have to write syntax to save it to a permanent file outside of work if you want to save it. But you don't pretty much ever need to do that. The only situation is when you're doing a bunch of data manipulations and you want to send like the finished product to somebody. In that case, the way that you would do that, see, do I have an example in here? I don't think I do. So this step right here that we skipped, in this libname thing, this is creating a new library, in this case called sassave, and it's the same place that everything else is. So if I run that, go over to Explorer, in my list of libraries, I have now added a new one, and I would have to put things there because that's permanent. Work is temporary.
It's permanent for your virtual desk.
It's permanent in that the files will live on your hard drive because they're tied to a specific place. So in this case, I'm using the same place because I want everything in one folder, whether it's a SAS data set or not. The way that you do that to save it, for instance, would be data SAS save, final version, we'll call it that, right? Set is where it's coming from, and it would be work.say GSS. So then this is save as, but you're starting with this. You're saving it as this in this permanent directory. And then it stays with you outside the virtual desktop. Yeah, I have to laugh whenever I hit final version. How many of you have files in your collections that say things like final version 7? Final version plus someone else's changes. Yeah. Never say final. That's just, you're asking for trouble. But, all right. Other questions? Okay.
I have a question.
Sure.
So I just popped into the homework and it said, copy the text into Stata.
Yep.
Like, how would you go about doing that?
Okay. Great question. So let me go to what you're looking at here. So in the homework portal, let me get my fake login. 1, 2, 3, 4, 5, 6, 7, 8. Begin or continue. So for whatever reason, the websites won't let me post files that have an SAS extension or a do extension. It just doesn't like that, and so I copied it and turned it into a text file. So for instance, if I want to do SAS, I click on that, I get this. I'm going to hit Control-A and copy. And in SAS, once you're in an editor like this, the little white thing here is new. You do that. I'm going to hit paste, and that starts off. So then all you have to change is this information right here. Put your ID in, which homework it is, and where you downloaded your data to. So this is what it looks like on mine. And then everywhere else, it will understand what file you're using. In Stata, it's similar in origin, a little bit different. So let me go back to, so Stata do file, this thing. If I want to make a new one, go to the website. Stata syntax looks like this. Same process, copy, go to the new do file and paste, and there it is. And here, I couldn't figure out how to make it take everything in one step, so you just have to change where your stuff is, which homework it is, and what your number is that goes here. And then it will import a CSV file, and you'll be able to do everything with it. So I'm giving you the labels for everything to start with, that way you know what all the variables mean, and you can open up the CSV data file in Excel or any other spreadsheet program. So you'll get one of these starter files for every homework that we have. All right. Other questions? Does that help?
Yes, but I was too busy looking at SAS. Can you just show me one more time how you got to that new page where you entered all the info?
So
I'll come to office hours on Thursday, don't worry.
well, Thursday I'm out of town.
I'll come
Next
to office
week.
hours next Tuesday,
Yeah.
don't worry.
Yeah, so in Stata, I wish I could, I don't know why it's doing this, but within that window, there's a open command, like a regular Windows, but you can also get to it within here. You just need a new, it's called a do file. Yeah, like you want to do something, then it's, and then you just paste it in. And then you save this as wherever else your data set is to go with it. So yeah, it's .sas in SAS, and it's within the same set of windows. Like in SAS, the .sas file shows up on your list here, and it's all within one thing, whereas Stata, the do's are in a separate window. And Stata apparently heard me talking shit about it and is not cooperating. So, fine. And yes, we should have plenty of time to get the first homework done, so no stressing. Remember that we're here to learn a language, right? We're learning vocabulary words like parameter and univariate, and then the notation that goes with those things like y bar and y sub I. Well, guess what? This is another language that goes with these things. It's how to tell the computer what you want. And the good news is that once you learn one program, it gets a lot easier to learn the others. It really does. The first one is the hardest one. Okay. Any other questions? All right, well then let me clear some of this stuff out of memory before it loses its mind. All right, bye-bye, Stata. Thanks for playing. And I think we'll get rid of all that, get rid of that. And bye-bye, SAS. Thanks for playing. Yeah. That was 0. Zero was due yesterday. Yeah, that's the one over the syllabus. And if you haven't done it yet, go ahead and do it. It's fine. I just want to make sure that everybody can use the system. That's all, before we get into anything serious. But yeah, homework 1 is due the 23rd. Let me pull up the schedule again. It was originally due the 16th. I bumped it back. so that we make sure that we have time to go over all of this stuff. And yes, I'm not here on Thursday, so that's where I'm encouraging you to sit somewhere comfortably with a beverage of choice and get this stuff to run. So, all right.
Yeah.
Are we ready for some new stuff?
Oh.
Yeah! No, for real, it'll be fun. We're getting into stuff that's actually useful now. So answering research questions with data, that's the idea. So it's a mouthful. Lecture 3 I'm calling Significance Testing in the context of univariate statistics and bivariate association. So we're getting to the point where we're learning how to answer questions about variables, which is why you're here. So 4 main topics here, talking a little bit about transformations because those are often done for convenience, preceding statistical analyses. Types of hypothesis tests that are about univariate information, just to get you used to the idea of hypothesis testing. Then moving on to bivariate, measures of association and their associated tests. And then a more theoretical sort of wrap-up of what we just did in terms of the way that we can screw up the conclusions we've made in terms of hypothesis testing. So let's, this lecture will take us a while to get through. That's okay. It's a biggie. So first topic, transformations. Variables that are quantitative often have somewhat arbitrary scales. And making sure that 0 means something is going to be important. It's going to color how you interpret the rest of the results from your models. So one of the first things that we will do in putting predictors into models is make sure that they have a meaningful 0 point. So as an example of a linear transformation, I give you centering. The idea is that you are subtracting or adding a constant to every case so that you're shifting the scale of the variable. So for instance, if I had a variable that had a mean of 5 and a standard deviation of 4, so x in this case is normally distributed, if I subtracted 5 from all of the observations, I've just moved it over so that the new mean is 0. It doesn't change anything. It just shifts it over so that 0 is a meaningful value. That's what's known as a linear transformation. All of the variables' values are adjusted in the same way. It's just a shift. In contrast, nonlinear transformations, such as the natural log, they change variables' values unevenly. And now, honestly, I had to look up this definition so I wouldn't screw it up, because I'm like, yeah, a log is a button on my calculator, right? I know what it does, but I'm going to turn around and read right from the screen. The logarithm is the exponent to which the base must be raised to produce a number. Okay, the one that you will always see in statistics is the natural log. It's a nonlinear transformation that is designed to take skewed variables and render them less skewed. That's what it's for. So for instance, if I have a variable that looks like this, it's positively skewed. There's somewhat of a pileup on the lower end. If I take the natural log of it, it looks like this over here on the left instead. So it does 2 things. It takes the lower values that are close to 0 and spreads them out towards negative infinity. So it never quite gets to 0. Everything has to be above 0 to be defined. And it takes these values that are skewed and kind of reels them in. So the log is used to keep things positive. It shows up in a lot of different places, but for here, I just wanted to show you an example of what a nonlinear transformation would do. So the original variable and the log transformed version are not going to be correlated perfectly. You will see this happen to try and reduce the influence of extreme values. So people may use the logged version instead because they don't want these people clear out here to artificially color their results. So that's a nonlinear transformation. Probably the only one that we'll use. Another type of linear transformation that shows up very commonly is Z-scoring. Z is another special letter. A Z-scored variable has a mean of 0 and a standard deviation of 1. So for each value, you would compute what x originally is. You would compute the z that goes with it by taking each x, subtracting the sample mean of x, and dividing by the sample standard deviation. Programs will do this for you. It's called Z-scoring. So it doesn't change the information of the variable. It changes everything evenly. So for instance, the original variable over there on the left looks like this if it's Z-scored. Same shape, same relative distances between the observations. The difference is the x-axis. So it's a linear transformation. Why would we do this? To try to make variables more comparable. For instance, if I have a blue variable here with a mean of 3 and a standard deviation of 1, and my red variable here with a mean of 7 and a standard deviation of 3, what if I wanted to pit them against each other in terms of how well they predict something else? Well, the scale of their prediction is going to be a function of their scales themselves. To try to put them on sort of more equal footing, you can z-score both of them, and then they both have the same mean and the same standard deviation. But it's a linear transformation, so the z-scored version of each will be perfectly correlated with the original variable. You haven't cheated, you haven't done even like destroyed the information in the variable. This z metric is going to show up a lot from now on. Not necessarily z-scoring, but this metric of mean 0, standard deviation 1. So remember standard norm, or do you remember normal distribution? Remember this picture? Normal distribution, you got to know two things to know what its shape is. The mean, the middle, and either the variance or the standard deviation. Quick reminder, how are those related to each other?
The variance is a standard deviation squared.
Yep.
Yes.
Variance is standard deviation squared. They are both measures of dispersion, right? The width of the distribution. So if you make a normal distribution have a z-scored scale such that the mean is 0 and the variance or the standard deviation is 1, that becomes a very special thing called the standard normal distribution, and it looks like this. So the new formula, given that the mean is 0, is based on z-scores instead, and this tells us how frequently each value of an observation is likely to fall if it follows this distribution. So mean 0, that's most likely. Within 1 standard deviation on either side, 68.26% of the observations are likely to fall. So this is the part where this is the math that someone else figured out and you can just trust them. But that's the formula. Within 2 standard deviations, about 95% of the cases are expected to fall, and 99 and some change within 3. So we know that anything past, say, 2 to 3 standard deviations in either direction is really, really unlikely. And we can use this distribution to quantify just how unlikely something is. Have you seen a table like this before?
Oh my gosh, yeah.
He's like, oh no. Yeah, no, we're not doing this. I just wanted to show it to you to link what we're gonna do, because nowadays you have computers. But what this table is telling you is for any specific z value, what the area under the curve to the left is. So basically, how much area is covered. So if I have a z of 0, that's 50-50, right? If I have a z of 1, that's 50% plus 34.13% that's under this curve. I highlighted one number because I'll use that in a token example, and then I'll show you what I would actually use this thing for. So let's say hypothetically that I give a test and I have my test mean that's 100, my test standard deviation that's 15. And I decide arbitrarily that I only want to give an A to 10% of my students. Note the star. I would never do this, but this is just an example. How do I figure out where the cut point is? Where 10% of the distribution would be expected to be? Well, I can use this back of the book Z table, find the z-score that is associated with 10%. So that's where I highlighted this number right here. This is as close as I get to 90%, and that goes with a z of 1.28. So the area to the left of this line right here is 90% of the distribution. The area to the right is 10%. I can take that Z-score formula and work backwards. Here it is, right here. So if I know Z, I can work backwards to get what X is. So the mean of X, which is 100, times the Z-score that I need, which is 1.28, times the standard deviation that I'm plugging in, which is 15, that works out to be 119.2. So that's the point on my variable at which I can expect this 90-10 split to happen. So that's the kind of exercise that you would have to do in an introductory stats class. What would I do this for? Let me show you something that's a little bit more realistic. To make a confidence interval. So whenever you are describing a univariate statistic, we need to know two things, right? What do we think the answer is? That's its estimate. And how much do we believe in it? Its precision. So standard error is imprecision. That's the thing that we would estimate to show our level of belief. And we can use that standard error to make an envelope around our statistic to say how variable we think it would be across samples. That envelope concept is what's known as a confidence interval. So for instance, if I want to build a confidence interval to describe the range of uncertainty around my sample mean, I need to know what the sample mean is, that's Y bar, and I need to know what its standard error is. So S, what's S again? Standard deviation. What's N? Not mean. Sample size, yep. So yes, in reports, APA style says that you can talk about the mean as M as an abbreviation. Standard deviation is usually SD, and sample size is N. So those are terms that everyone will recognize such that you don't necessarily have to spell them out. Standard error you will have to spell out, by the way, in a table note or something like that. So in terms of calculating this window of uncertainty, we need to know three things. First, which sampling distribution to use. There's choices to be made. Let's do Z for now because that's the only one we've talked about. Do you want an interval that goes both above and below your estimate, or do you want it to go on only one side? Almost always you want both sides. That's what's known as a two-tailed, we'll say test or interval in this case. One-tailed is only appropriate if the other side legitimately doesn't make sense. And I have a star on here because I actually got into a Facebook fight recently about this. I'm part of a group called Academic Mamas on Facebook. Give them a shout out. And they ask questions of ourselves, everything from how do I sleep train my toddler to my advisor told me that I should use a one-tailed test and then my article got rejected and the reviewer said it should have been two-tailed. Can anyone weigh in? And so I'm like, oh, no, two-tailed, always. I'm like, but it's not your fault. Plenty of dumbasses probably teach it the wrong way. And someone else wrote back, well, plenty of us non-dumbasses teach it that way too. And I was like, oh, hell no. And I was telling my husband about that. He's like, just let it go, don't make it worse. So I didn't respond, but everyone else in the feed, for the most part, agreed with me. And she said two-tailed was the way to go. So I'm like, yeah, one-tailed is for situations in which the other side doesn't make sense. That's the only situation. You don't get to stack the deck. Otherwise, if you have a hypothesis, that's going to be my belief. So I'll just put that out there. I'll show you examples of that as we go through here. But it's two-tailed or bust as far as I'm concerned. So how confident do you want to be is the third thing. How big do you want your window to be? Do you want to be 90% confident? 95%? 99%. The window itself then is computed as the estimate. So for instance, the sample mean. It includes plus or minus the standard error of that estimate, such as the sample mean, and then Z critical. That's this, go back, the Z value that goes with how big you want your window to be. So for instance, a 90% confidence interval uses a Z value of 1.65. 95%, which is probably the most common, is 1.96. and 99 is 2.58. You don't have to memorize these. Software will ask you for this side, and then it will do the rest for you. So this is another thing that I had to look up to make sure that I didn't screw it up, because it's very easy to screw up the definition of a confidence interval. What does this thing mean once you have these two numbers? It is the interval in which the true population parameter, such as the population mean, is expected to fall 95% of the time if we redid the same study over and over and over again. That's what it means. These are alternative explanations I took out of your textbook for examples of how not to say this. But it's a statement of how much you believe, essentially, that you have captured the population mean. Let's say it that way. So here's visualizing what these cut points would be. So if the population mean is here, and you found something that's like over here in this orange, right? It's not very likely if the population mean is really this. It's too far above to be likely. Same thing over here if you found it over in the blue. It's too far below to be likely. So the one-tail versus two-tail has to do with whether you want to allow the possibility to be wrong in either direction or just one direction. Because you get twice as much area and you can move your critical value back if you ignore one side. So the cut points then allow more area to be expected for a larger interval. To complicate matters somewhat, this confidence is also referred to as its complement, as alpha. P-value and alpha functionally refer to the same idea. It is what's left. So if I have a 90% confidence interval, I have an alpha of 10%, or a p-value of 10%, the probability of observing a value more extreme than what we saw. If I have a 95% confidence interval, I have an alpha or a p-value of 5%. So just to give you a sense of when this can get confusing, in SAS, it asks you for your alpha level for these things. Stata asks you for your confidence level. The option is level for both, but you have to know which one it's asking for by the documentation. So being able to go back and forth easily will help you. So here's an example of when I would do something like this for real and have. Anybody interested in genetics in here? Yes? No?
Like I'm interested in twins, but not like I study it.
Okay,
Just
well,
curious about it. I shouldn't have raised my hand so rapidly.
that's it looks like I'm interested in twins too if you look on my CV, but it turns out I'm just interested in data. And I have a longtime collaborator who has longitudinal studies of twins. She studies specific language impairment in particular. This is a recent study from Mabel Rice. There I am, fifth author. Woo! And she was interested in something called the twinning effect. It has been suggested and demonstrated a little bit, not very robustly, but a little bit, that twins have developmental delay relative to singletons, in language especially, and in I think a few other things. But it's a delay that goes away by the time they hit like elementary school. So this was one of the first studies to have a huge sample of twins. It was from collected in Australia, following them from age 2 to 4 to 6. And so this is a paper covering ages 4 and 6. And so the demonstration of whether or not this sample has a twinning effect, that was research question 1. So here is a subset of table 1, which listed all kinds of measures of language. This is the PPBT picture Peabody vocabulary test. Does that sound right? No one's going to correct me? All right, well, I'm the linguist in here today. Hooray. At age 4, MZs and DZs, monozygotic and dizygotic, fraternal or identical, respectively. And this is the sample mean on a test that is normed so that at every age you have a mean of 100 and a standard deviation of 15. So that is like the population. In this sample, the mean at age 4 for DZs was 96.78. The standard error for that mean is 0.6, 93.9, 0.9, and so on. the mean plus or minus standard error times z critical. In this case, it's a 95% confidence interval, which is a z critical of 1.96, gives us this interval right here. So I have highlighted this last one, for instance. So you can see the math down here. So in this case, the population mean of 100 is within the interval. So it doesn't look like this sample provides us with any evidence for twinning in this set of people, and for this at age 6 in MZ twins. However, the first two rows do show an evidence of twinning in that the confidence interval does not include 100. So it is really unlikely that we would find a sample mean of 96 or 93 if the population mean were 100. So this is the kind of thing that you would use the standard error of the mean for, is to test this type of hypothesis specifically. So if you want to know exactly how unlikely it is, we can do our very first hypothesis test. Answer. This is what's known as a OneSample Ztest. I'm trying to calculate the z value that is implied by this sample mean using the information from the sample. So my z formula here, y minus the population mean divided by the standard error. If this is not something that we know from the population, we can use our current data for it. So here's for this one, 100.28 minus 100 divided by 0.79, that's my standard error, gives me a z of 3.35. So that is, go back to the table here, z of 0.35 would be like, oh, just right there. So, does it seem like it's pretty likely that I'd find a mean of 100.28 if the population mean were 100?
Yes.
Yeah, that's well within expected, or random is expected fluctuation in that case. So yes, we can quantify then what the area is at that level of z. So 72.64% of the time, we'd have a z value more extreme than plus or minus 0.35. I say plus or minus because it's two-sided. We're allowing the area to reflect that it could have been above or below, and we didn't know it was going to be above until we got the data. One-tailed p-value would be to take that in half. So I got these probabilities off an online calculator, but this is something that we're going to ask the software to do for us. This is not something we're going to look up in a table or otherwise do by hand. So two of these showed the twinning effect in that the mean was significantly below the population mean of 100, but this one showed the opposite pattern. The mean is significantly above. Population mean is 100. Observed standard error of 0.45 gives me a z of 4.29. So is that extreme or not extreme? What do you think? Extreme. Yeah. That is clear out here somewhere in the tail of the red. So if the population mean was really 100, we would get a sample mean of 102, like hardly never. So it seems like that's something. That is unexpected. So I had a question, I think, at the end of last week. What would we use standard errors for? This is why. To be able to say how far off our estimate is of something from what we expect. Okay. How are we doing so far? All right. So, what could go wrong? Beer to the rescue. True story. No, I'm serious. Turns out that this z-test thing doesn't work very well. So I've given you the full story here and the source for it. There was someone named William Gossett who was working for Guinness Brewery, and his job was quality control. And he was testing hops for like hoppiness. I don't know what I'm not a beer person, but apparently you want like a certain amount or else it's no good. Yeah, good enough? Okay. And so he was doing all of these tests on very small batches because it took a long time to do the batch. And any batch that he flagged as being outside the target region, they did more extensive testing on. And it turned out that 3 times more than he had expected, the samples that he thought were broken were actually okay. And so he's like, And he asked Guinness to go do some professional development. He went and got himself a graduate degree in statistics. Yeah. And, he's really dedicated to his beer, right? This is an extreme level of dedication. So he did a simulation study by hand in which he derived a new distribution. He wanted to publish it, but Guinness had a policy that they don't allow their employees to publish because they didn't want them giving away trade secrets. So he did so under a pseudonym of student. And that's how we get student's tea. Thank you, Guinness, in beer. So, yeah, the T-test, exactly. We're going from Z to T, but that's where it came from. So again, trusting the people who did the math, I'm okay with that. He derived empirically using flashcards what this distribution should look like, and someone later came along and did the analytics and said, yeah, he nailed it. Oh my goodness. So here, the black line, that's what Z looks like. If you correct for the sample size, the less cases, the fewer cases you have in your data set, the flatter T gets. The more area is out here, which means it's easier to find something to be noteworthy or unexpected than it should be. So for instance, degrees of freedom equals 6. Degrees of freedom is a new term that we're going to talk about here. At this point, it's just sample size minus 1. It gives you a new set of cutoffs given your degrees of freedom and given your alpha. So this is the uncertainty leftover area. So P equals 0.05. That means 95% certain. This would be 97.5, 99, and 99.5, I think. It gives you the new critical value. And note that all of them are well above what it would be for Z until you get down to about n of 120, and then infinity is 1.96. So from now on, Z is gone, and T is our new friend. Because worst case scenario, they're the same. So everything is going to give us T's. Question?
No Z's.
Z's are gone. They're dead to you. Z should only really be used if you know the population standard deviation. And we'd never know that. So, yes.
So are we going to have to do Z's?
No. One tiny exception when we're testing a one sample proportion. That's a Z because the variance is fixed. You can think of T's and Z's as interchangeable. Basically, it's which reference distribution is it comparing your test statistic to? Is it flatter or is it the tall one? And at some point, once you get past, you'll make the same conclusion most of the time past about 20, right? If you look, these sort of start to asymptote. So it's only in really, really small samples like what he was working with where these results would be very different if you use T versus C. But yeah, it's going to be T pretty much from here on out. All right, so degrees of freedom. What the heck is that? Have you heard this term before? A few people have? Okay, do you understand what it means? I didn't. I know, it's well, it's a thing you have to memorize. It's n sometimes, it's n minus 1 sometimes, it's n minus 2 sometimes, Well, it turns out there's a reason. So there's 2 kinds of degrees of freedom that we're going to need to know in this class. There is numerator and denominator. What we're talking about here for T is what's known as denominator. And that shows up, for instance, literally in the denominator for calculating the mean and the denominator for calculating the variance. Denominator is a function of sample size. Numerator, which we'll get to in a minute, is the number of things that you're testing simultaneously. So where this comes from is the idea that this gives us all an index of how many different statistics we could compute to perfectly describe our sample. So I don't necessarily need to calculate a mean or a variance, right? I could make up the Lisa parameter, and that is the effect of being a Lisa. And it perfectly explains my value relative to y'all's. right? Then I could make up the col parameter, and it's going to do the same thing. And I could give each of you your own parameter, right? And we would perfectly describe everybody's value on some outcome in this class. I could do that. That's not very helpful or useful, but I could do that. So with that as sort of the starting point, like giving us each one statistic that describes us and no one else, can we do better than that by calculating sample-wide things? So the analog to this idea, by the way, is found in Weight Watchers points systems. You familiar with this? Yeah, HATE. Can I do this for you? There's also, I remember this from when I was younger.
Now back to Deal a Meal with Richard
Deal a
Simmons.
meal.
We're back.
Richard Simmons, yeah.
Fastest growing weight loss
I
program
can't get the.
in its first 8 weeks.
Can you hear it?
250,000 people started it. What is it, people? That's right. But you know, I bet a lot of you out there
Yeah,
are
so
still
I'll
wondering,
narrate.
does
So
Deal
he's
a Meal
describing
really
this
work?
revolutionary
Well,
diet
everybody
program.
here is on it. What do you think? Does
It's a
Deal
2-minute
Meal
video.
work?
And
It already. Well, I can lose weight.
get to the point.
Meats
So
are
you
red,
get
veggies
a wallet
green,
of
fruits
cards.
pink, dairy blue, fats yellow, and
And
bread.
each card, like for different
You
food
start the
groups,
day with the
right?
set number
Beginning
of
of the day,
cards on the
with all
left
your
side of
food
your
in
Deal
your
a Meal
wallet.
wallet.
Every time you eat,
you
throw
buy
one
your
away.
food by moving the
Okay.
appropriate card to
That's
the
yeah,
box
that's the
on
done
right.
column.
When you're out of
Right,
cards
and
on the
when you're out of
left,
cards,
you're
put the
done
fork
eating
down.
for the day.
You're done.
With these cards,
Deal
you
a
can
meal.
finally control your calories without
It's Weight
counting
Watchers
them.
points, am I right?
So
It's the
does Deal a
same
Meal
exact
really work?
principle. But yeah, it's Deal a Meal.
Tammy, what do you think?
Well, Richard,
Yeah,
I
she's
have
a
tried
believer.
every diet. None of them have worked.
So
Then I
yes,
saw your
there's the
ad for Deal a Meal,
infomercial
so
from
I
Deal
thought
a
I'd
Meal.
give it a shot.
Well,
I know. I miss the 80s. But it's the same idea. Like, you want to spend as few points as possible so that you can lose weight and not starve yourself. So every time we estimate something like a mean or a variance, we spend a point. Every time I make up a Lisa parameter, we spend a point. The col parameter spends a point. So this is like how many points left. This is how much food you get left to go about your day. And the more you eat, the fewer your degrees of freedom. So we start out with n to get the mean. If we need to use the mean in the formula for variance, we used 1. The next time we use variance in something, we lose another, so it's 2, and so on. So this is how many parameters left over you could use, how many points left over. Degrees of freedom. So in this example, it's just n minus 1. For instance, other uses of t, it'll be n minus the number of parameters you had to estimate to get to that t. So n minus 2 sometimes, 3 sometimes, 4 sometimes. It just depends on the context. So yes, degrees of freedom in the denominator is to Deal a Meal. How's that? Maybe? Yeah. Well, for those of you who don't have no idea what I'm talking about, good. Diet culture is a terrible thing. But it makes for a good analogy. So intermediate summary, what we have talked about so far. We've taken one statistic, such as the sample mean, and using its standard error, talked about how to make a confidence interval around it. We get to choose the distribution. It's going to be t, pretty much forever and ever. How much coverage we want. We can also do a significance test as to how disparate that sample mean would be if the population mean were really true. That's a OneSample Z. We can also do the same thing for other statistics besides sample mean. And all of that will require software, which is what I want us to do next. So let's see an example. Not inside the virtual machine, but inside Word. So this is example 3. If you don't have this open, please do so. We'll go through portions of this today, and then next week we'll pick up the rest. So this is what I'm going to do the rest of the semester rather than fighting with the virtual machine live. I have compiled for you a handout that has both syntax and output and my own annotations as to what is important. So I've hoped to write down almost everything that you would have written down so that you can just follow me, but feel free to make your own notes as needed. So for this example, demonstrating what we just went over, I've selected a random subsample of the GSS dataset of 100 cases. That way we can, the plots and such will be easier to use. And I've pasted in the sections of syntax here that are relevant. So file save in SAS, telling it where my stuff is. Changing the name of the dataset to whatever it is I want to import. In this case, it's GSS subsample. These files, by the way, if you do want to play along, are available right here under example 3, SAS and Stata files. I have the original dataset, both syntax files, and the output that the syntax files create in here so that you can see the originals and run them along at home if you wish. Same thing in Stata. File save being defined as my place, and then using it to open up the dataset. So I'm going to show you an example first of linear and nonlinear transformations so you can get a sense of what those do. In SAS, what is this line I'm staring at right now? Data and set. What does that do? Feel free to read from the screen.
Save as itself.
Yeah. Why do I need that?
To make a new variable.
Yes. And what happens if I forget it?
When you come back again, it won't be there?
Nope. It will just yell at me. It will yell at me in red font because it doesn't know where to put my new variable. So in SAS, because you can work with multiple files at the same time, you got to tell it which one to do stuff to. If I wanted to make a new data set instead, which of these would I change? Data or set? Data. Data is make me a new data set. Set is from. So this, instead of saving as itself, would save as a separate data set with the 2 at the end. Superstitious people sometimes like to do that because that way they can always go back a step if something goes wrong. By the time you're finished, you'll be up to like subsample 10, but that's fine. So here's an example of a linear transformation. We saw this earlier. Taking family income, which is scaled in dollars, and changing it to thousands of dollars. Here's an example of a nonlinear transformation, taking the natural log of family income. Note that I'm adding 1 because you can't have the log of 0. And I didn't know if I had any zeros in the data set, but I wanted to make sure that it would work for everybody. And then last but not least, I am making a copy, putting a Z on the end because I need to make a Z-score in a separate procedure down here. So here's another proc. Proc standard. It standardizes. So you tell it what data set you want to work on. So note the difference in the colors and this right here. This data is dark blue, whereas this data down here that I have highlighted is a lighter blue and it has an equal sign. This second instance of data is an option within a proc. And that's why you need the equals. You don't need the equals up above. That's all you're doing is referencing a data set. It's going to create a new data set that I'm just labeling GSS, and I've told it how I want my variables standardized, mean 0, standard deviation 1. In addition to Z-scores, you might also hear about T-scores. You heard those before? T-scores is mean 50, standard deviation 10, I think. It's just a metric that some people know what it means and they find it convenient. Another example you're familiar with, GRE scores. What's the mean GRE score if you took it, when I took it? 500. What's the mean nowadays? 150, I think. Same idea. It's a linear transformation. Different scales mean something to different people. So at this point then I have a new data set in which FAM Inc. Z is the Z-scored version. To do so in Stata is a little bit more straightforward. There is gen is used to make regular new variables versus egen, which is used to make fancy new variables. Like anything that's more than just a simple linear transformation is an egen. That's what I figured out. So I looked it up. So all of the things for Stata, pretty much I had to ask the Google to find it, because I don't have the stuff memorized either. But STD for standard makes a Z-score. So let's see how to get information about these variables. So proc means gives me descriptive information, univariate statistics for quantitative variables. So I have all of the versions of family income here, so you can compare them. So the mean family income originally is about $39,000 with a very wide standard deviation. It ranges from $245 all the way up to $155,000. If I take all of those numbers and divide by 1,000, it's just moving the decimal place over 3 digits, just as you would expect. It's a linear transformation. Fam Inc. Z, note mean exactly 0, standard deviation of 1. That's the definition of a Z-score. So we know that 2.5 is a really unexpected value for a Z-score. It's way out in the tail. 95% of the distribution is within plus or minus 2, so 2.5 is getting out there. And then log, it's somewhere between 5 and 11 in log scales. The log is not have an intuitive scale. But let's see what the pictures look like if we make histograms of these. So proc univariate, suppressing all the extra output I'm not interested in right now. Here are the 4 pictures of income. One of these things is not like the other. Who's the oddball here? Log, why? This is the nonlinear transformation. It takes the extreme values and reels them back in on the right side, and it takes the pile of low values and spreads them out on the left side. In practice, what you would use log for is to make a variable that is bounded, like this. You can think of this as a count, because it can't go below 0, and it makes it into something that's more continuous to be predicted more easily in a model. In practice, that's what you would use it for. So it shouldn't matter in the analyses that follow which version of family income we use out of this 3, original, scaled in thousands, or Z-score, because it's the same. But log versus any of the others will give us different answers because it's a different variable. And here's Stata's code to do the same thing. Now making inferences. Let's play with some variables in this data set. One is variable that it gave us is years of education completed. Let's say that I have a hypothesis that I think the population should have 12 years of education. Let's just say. I'm just making shit up. It's fine. It's called a hypothesis, right? It's my belief about a phenomenon. I think that if the general social survey were representative, then the population mean years of education would be 12 years. That's my thing. Well, let's see what happened relative to that.
Lisa,
Yes.
class ended.
What?
Class ended.
Oh, when?
45.
Oh, yeah.
Thank you for telling
You
me.
said you were gonna start something, and I was like, I don't know how long it's gonna take. Whatever you're about to start, go.
12th one, yeah, you're right.
Yeah.
Sorry, I get so like into this. I don't have my schedule yet. No, thanks for telling me. I'll shut up now. Okay, but I will see you all next Tuesday for the exciting conclusion. I'm gonna have to like set an alarm on my watch or something. Yeah, well, they're waiting on me, so, right? It's my class. Question?
Yeah. Yes.
That's the one thing I guess. It wasn't.
You have to give her the foundation, and then like, okay, now it's like that.
About the process. So you didn't really mess with
Do you have questions?
I think it's for what?
What do you mean by file, but you can.
Did you get my email? I did, I did it. I just have my. Yeah, I don't know my.
I have to actually check this project comes in and the math knowledge. You know,
so the data.